So this chemist, if we peek in on him, is not too happy. It's a chemoji called Failed Experiment. It's actually supplied by the ACS. That's the ACS logo on his lab coat. And we could see what's in his hand. It's kind of going a little bit awry. He has this black color is something we usually call tar, but there's a lot of it. And so that's needless to say, that's a source of frustration for a lot of chemists. Now, things that make chemists happy: building new molecules. That's really fun to synthesize them. But as part of those synthetic steps, we always need to purify. And you often hear them kind of jokingly complain about that, but it is really expected. So, for example, most of the samples we encounter in lab are either solid, so this could be like the crude solid, or liquid. And if you've noticed by now that the common sort of appearance of organic molecules is usually not colored. If it has any color to it, that's a cause for discussion. What's causing that color? Is it conjugated? Is there some sort of transition metal? What's going on in there? If we don't have a good reason for a colorful compound, it's usually an assumption actually that color means there's an impurity present. We usually expect colorless or white sort of samples. So in this case of a solid, we expect it to be white. In this case of a liquid, we expect it to be colorless. So this chemist is going to have to purify them. And so we know from experience that once we're done with the purification process, what to the more untrained eye would just look like a boring old colorless liquid or a white pile of solid. And this is these are beautiful crystals obtained by a former student after a recrystallization procedure. That this actually brings much joy. There's a great deal of satisfaction that comes to chemists when they accomplish that feat of going from the crude products to the pure isolated compound. So these are confirmed by spectroscopy and TLC to be pure, and once that's confirmed, and by appearance gives you that initial indication, and once that has been confirmed, that's usually a great feeling. So we're going to continue talking about more purification techniques today. So let's look at this chart, putting it all together. So you're faced with the same samples that chemist is, and you have to say, well, how do I know how to get to this phase? So you have to judge which of the following techniques is appropriate based on what you're starting with. So if you're starting with a solid in a first year organic class, these are the techniques we would use to consider separating the solid from its impurity. So the solid, the assumption is the solid is the main component and it's contaminated. So it could be in a liquid, and as long as it's insoluble, you do a simple vacuum filtration, right? Buchner funnel collects your desired material and you get your crystals. But if it's not ready to collect because we could see that it's still got color kind of tinge to it that's not really supposed to be in its final product form, then recrystallization is the way to go. Once again, that relies on solubility in a different way, so you have to try to find that solvent that's soluble at low temperature. Insoluble. So like at ice, the crystals would form, but at high temperature, you get it to dissolve, and that act of recrystallization will allow you to get some nice pure solid out. Sublimation is the transition between solid and gas. So naphthalene, for example, sublimes quite easily. So if you're able to heat it slowly, the solid, it will transition straight to gas and bypass the liquid phase if the pressure is less than its triple point pressure, which happens to be the case for atmospheric pressure for naphthalene, and some others, by the way, like carbon dioxide dry ice. So that's why we see the sublimation happen so readily. So here's the solid category, but let's say we're faced with a liquid. Gravity filtration, in contrast to vacuum filtration, you keep the opposite. So in vacuum filtration, you keep the solid and you dump the liquid. In gravity filtration, you dump the solid that's collected, and the liquid is actually what you want. And so we've done this before with the case of using, removing a drying agent, for example. Extraction, that's liquid, depending on miscibility. You exploit pKa differences. Usually you're getting something to ionize so that you can get an aqueous phase and that sort of thing. Chromatography that exploits attractive and forces, which includes polarity. And so you just want to remember to run a TLC to determine what your solvent ratio is. And chromatography can really do almost anything. So it's a great separation technique. But the one we're going to focus on today is distillation. And so this could be, it starts off in a liquid form. There could be a dissolved solid that we want to remove. Like we could distill seawater to have the salt separated from the pure water. But oftentimes it's actually two liquids that are mixed and you need to separate. So if you have two different liquids, then you need to have your boiling point difference between those two liquids greater than 30 degrees for simple distillation to be effective. There are other types of distillation we will cover later that can separate at a narrower boiling point temperature range. But the one we're focusing on today is simple distillation, and so the goal is to have that boiling point difference of 30 degrees or greater between the two liquids. So that takes advantage of that physical property. Once again, moving on, we are going to presumably assume that we're starting with the crude sample and be very happy when we get our nice purified product. So this is a distillation apparatus. And there's a lot of parts to it. So they're all labeled here, and this is a actual video that's linked up in the Prelab requirements. So be sure to go ahead and watch the full thing so you can see the distillation in action. This particular experiment was the separation of methanol and methylene blue. Methylene blue is an organic dye, so that's hence the blue color. And methanol is a colorless liquid. And methanol is very volatile, has a much lower boiling point than methylene blue. But that's something that would be looked up prior to starting the lab, part of the pre-lab procedure. And that idea is that if you boil those, that methanol would boil first, hence as it travels up as a vapor, can be trapped before methylene blue makes it up the same path. So let's go over the parts that are necessary. We have our heating mantle to warm the round bottom flask. This is called a lab jack to help raise because notice this height difference here, and just to kind of stabilize it and keep it raised up. These are really useful when you need some extra support. There's always a clamp around the neck of the round bottom flask because that is the most important one to not let fall, but because it has their hot liquid in there. So you never want that to be unsupported, but it's kind of nice to have the secondary support there. And then this is the still head, or also called distilling head, this joint. And notice where they connect. This is called a ground glass joint. It's kind of opaque in comparison to the rest of the flask. So it's been kind of filed down to be a little bit more, or etched, to be a little more, have a little more traction. And it's really important that the inner joint fits in the outer joint and matches those sizes. So in our lab, we use 1420 or 1922. That's the inner diameter versus the outer diameter. But you want to always check those to make sure they're snug. So no air can get in or out very easily. And then they're usually greased so that they don't stick. And then here's the thermometer adapter. And so that's a separate piece of glassware because you could see every time you see a ground glass joint outer diameter, that means there's an inner diameter as part of that. There's the thermometer to monitor the boiling points. Notice it's not immersed in the liquid. The thermometer is hovering at this intersection right here. This is the path that the vapor can travel. So let's check back in the thermometer in a minute after we look at the rest of the glassware. So this is the condenser. We've seen this used in reflux. So notice their reflux usually has it up here. This is off to the side now. And so the cooling is happening here by the water coming in, circulating through, and cold water going back out into the sink. And so it's hooked up to a water line. So the vapor, once it hits this cool contact point of the glass, the idea is that it condenses and drips down and collects as a liquid in the collection flask or receiving flask. There's an adapter, since look at this right angle here. There's an adapter to help facilitate that. Some sources will have slightly different names for the different pieces of glassware, but this one's a receiver adapter because this is the receiving flask. I've also seen it described as the vacuum adapter because you can actually, this arm right here can allow you to hook it up to a vacuum line for vacuum distillation. So, but we're sticking to simple distillation today, so don't worry too much about what that arm's doing. Okay, so that is the general idea of what goes on in distillation. Now let's look at a few more details. So you got this boiling, you have two component system. The idea is that the desired component could stay here if it was the higher boiling point system, assuming everything else would come over. Or if you wanted the methanol, so if you wanted the methylene blue, then the methanol would come here and you'd discard that. But if you wanted the methanol, then you would discard what's left over in here after the distillation is complete. So notice that nice colorless liquid collecting here, filling up with methanol. So when this boils, and as long as you do it slowly and carefully and steadily, the methanol will boil up first before the methylene blue. And as it travels up as a vapor, there is no cold surface to slow it down. So it stays a vapor, might condense on the surface of the thermometer or keep going down this way. But the idea is that you want that thermometer strategically placed so that it is forced to interact and touch that vapor before the vapor can travel this way. That will measure the temperature of any component that comes in contact with it. So it'll have the temperature of air until suddenly you'll see the temperature rise very quickly. And students sometimes have a problem with that because it's submerged in the liquid. So to see the temperature change when it looks like something invisible is changing it is a little weird at first. I can understand, but yeah, you were watching for a rising temperature because it's nothing there. The hot vapor is coming up, and it would only be, the vapor must be the temperature of the boiling point of the methanol, otherwise it wouldn't have vaporized so readily, and it usually even condenses a little bit right there. And once you see it steady, because phase transitions, remember, have a plateau for the temperature at which they transition. So once you see a steady temperature, then you record that as the boiling point of the liquid. So this could be a way to identify a liquid's boiling point in addition to everything else. So then the vapor goes down here, hits the cold glass, cools, collects. So how do you know you're finished with the distillation? Well, might see that it's almost dry. By the way, you should never go to dryness. It could actually overheat and cause an explosion. So got to be very careful with that. But usually we don't leave it alone. Monitor it very closely so that what you see, anything left behind, you're trying to make sure you've got maximize your recovery, yet you aren't going in danger of charring everything in there. However, on that same token of monitoring it closely, you have to watch that temperature. If the temperature changes from its boiling point, so it should stay steady at the boiling point of whatever you're collecting here. If that temperature changes, then that means whatever's touching that thermometer is not this compound anymore, right? It's something else that has that boiling point, or it could be air. But on either way, you're done, so you should remove it so that you don't have a new contaminant coming over. Okay, so you're ready to do a distillation. What are you going to do? You're going to open your organic glassware drawer, and this is what you'd see, among many other components that you'd have to discriminate which is appropriate to use and not. So let's look at the pieces, and we're not going to focus on the electronics or the sample itself, just the glassware right now. So we have our starting flask. That's where our distilling flask is. This is our receiving flask. Notice it's smaller. You need at least the same size or smaller because usually you're collecting less, but do be mindful of that. If you our rule of thumb is that you shouldn't have to ever fill one of these round bottoms more than halfway because you're going to be boiling, and if it's full, you could easily have a problem where something would shoot out of it, and so don't go over halfway. And so if you have that halfway full, the worst it can do is fill this all the way, but that's okay because this isn't being heated, so that should be sufficient. Now I'm going to go ahead and give myself some room. I think I'll put it right in the middle. So what do I do next? Do I put the thermometer there? No, that's not going to fit. These are actually kind of angled on purpose. That's not going to happen in your drawer. Here we go. There's our distilling head. So distilling head, that allows us to have just that right angle so that when the vapor travels up, it can gravity can kind of help it ease its way back down to the collector. Now let's get that thermometer in there. That's what that red cap is up here. This is our thermometer adapter. They come in different shapes and forms. In our glassware drawer, we actually have an extra piece of glassware to do that. But this is like a little screw cap, which is pretty nice actually. And then look at this condenser. Condensers also likewise, I mean, there's like 20 different condensers, but they all have the same sort of function. They all have names, and West condenser and Liebig condenser and so on, but don't be too concerned about that. They're cooling, they're circulating cold water so that you can condense. So they have that same purpose. So notice we have the spot for the hose is to go in through the bottom, out through the top. All right, so we're almost there. So let's get our receiving flask. Can't do that without this sort of right angle bend here. And now, voila. So that is the assembly of a distillation flask. We would need to put a little stir bar in there, and it's ready to go. Okay, so here is the distillation setup once again with a different perspective. I know it's like a cartoon, but this is a really common application in which distillation is used. So I had you watch a video about whiskey distilleries because that's a really common application. Essential oil distillates are another very common application. And so essential oils come from plant material, and then the plant has those oils that everyone wants to extract out of there, but because oil is not soluble in water, you can't really get it to dissolve in the water. So you just kind of crush up the plant as much as you can and then have it in water, and the oils might kind of suspend in water a little bit, and then of course heating would help release more of them, and it actually co-distills with the water. And later, as you know, you can separate oil and water pretty easily. So that's done at a later step, but with an actual extraction, right? So you let them co-distill, and the water carries off some of the essential oil with it, and it collects over here. So we actually covered this particular experiment with how it co-distills. We call it steam distillation. I like this because it also will illustrate the flow of everything again. So turn on the water, then the condenser is cooling. That means it's safe to turn on the heat. So you can see it drain into the sink. Here comes the heat source. It's heating. We want to avoid reflux in this case. Reflux would mean the liquid just stays here, keeps going up and down. We want it to progress and distill. So we have it vaporized. We've approached the boiling point of water, which means it's going to start collecting and coming out here. And notice this collection flask is an Erlenmeyer flask, and that's just fine. So we collect more and more oil mixed with the water, also known as the distillate, and that is ready to separate. Back to a real life picture. This is the complete setup that we have in our drawers at Pierce College. So this was a student's distillation, and you can see some other nearby students have been working on some of that. So this was an action shot. So they have their round bottom flask with a stir bar, and so the stir bar is stirring and helping maintain what we call smooth boil, and the vapor travels up, hits we use these lollipop thermometers, so they have this metal probe, so it can measure the boiling point. You could record that. The vapor keeps coming up and goes into the condenser, turns into a liquid at this point because it is cool, and then it travels down, and it's angled in such a way that it allows the gravity to kind of assist with that path, and then it collects over here. And then when that fills up, you're ready to go. Notice there's clamps to support it. That's an important part of the safety. And the student looks like they probably just started or hadn't added it yet. One follow-up question we might ask about this setup is, why the stir bar? So there's no reaction, chemical reaction that's happening here. So we are not trying to mix our impurities. If anything, we want to separate them. So why do we have a stir bar stirring our impure mixture when we're not even trying to intentionally mix the components? So the answer comes by the fact that we're trying to, once again, maintain a smooth boil. So if you do not have any stir bar in there, or anything to break up that surface tension and create a nucleation site, like boiling chips or stones, and we've used boiling sticks for, when we're heating on a hot plate, that will cause what's a phenomenon called bumping, and that's something we want to avoid. So I'm going to spend a little more time on that in the next slide. Okay, so bumping is not desirable. So here is a flask that's heated without anything to stop it from boiling so vigorously. So bumping happens in homogeneous liquids. Look at how wild that's gone. They essentially superheat because the liquid's homogeneous and it doesn't have any nucleation site, which is, a site that kind of disrupts that surface tension that builds up as the heat increases. And finally overcomes that energy barrier to break the surface tension, and the rapid boiling ensues, and it could even escape the flask, which is not only bad in terms of maintaining purity and making the reaction go smoothly, it's also unsafe. And so to control and minimize bumping, stir rods or stirring bars are often added even if they're not needed to mix. But also there's something we have in stock called boiling stones or boiling chips. And so these help maintain these little pieces that you can just put in there. They look like little pebbles, and they just break up the surface tension so that there's a nucleation site for the bubbling to happen more smoothly.